Welcome to Spring LIB.
Hello everyone, today we're doing chapter 11, problem 64. So this is one of the more challenging problems of the textbook. And this asks us to draw the stepwise mechanism for the following reaction. So we have some sort of alkyne here, and we're reacting it with diatomic bromine and water to get this oxidation product here. So let's go through the mechanism how this happened. Well, first step, we need to identify the nucleophile and the electrophile. So we know that nucleophile is electron-rich source, so pi bonds can be electron-rich, and the electrophile is electron-poor. So the Br double bond is, or single bond is very electron-poor and electronegative. So this would most likely act as our nucleophile. So drawing the reaction mechanism, we know that the pi bond will go and make a bond with the bromine. When you make a bond, you break a bond. So this bromine will fall off. But at the same time, one of these lone pair electrons, so instead of forming a carbocation intermediate, that is prevented by the bromine just right away coming in and attacking the other side. So now you form some sort of intermediate like this. So this prevents the formation of carbocation intermediate. So make sure everything stays neutral. So this is pretty favorable. And you have Br minus coming out. So two things can happen. One can say that, well, your Br minus can now act as your nucleophile and attack one of these sides to form trans bromine addition. And yes, this is true if Br2 is the only reagent present. But here, we have this diatomic bromine in a solution of water. So there's going to be a lot more water molecules floating around than the single bromine that falls off. So we know that water is going to be the most likely nucleophile. And because of the electron-poor nature of this carbon, we know that the water will attack on the more substituted side, making a bond. So when you make a bond, you break a bond. And that bromine will pop out to this terminal position that we see in the products here. So now with the addition of water, you have now this water that attacked, but now it's positively charged. But to neutralize this water to make it into alcohol, we can use this bromide ion that fell off to form now this enol form structure here. Remember, an enol is a pi bond directly bounded to an alcohol. And now we need to oxidize this enol to its ketotautomer, which is the product actually. So if we use one of the lone pair electrons on the oxygen nucleus, we can make a bond, a new carbonyl bond. When you make a bond, you break a bond. So this pi bond, with its two electrons, will go through the carbon nucleus and pick up this proton. So it picks up this proton to make sure everything stays neutral. So oxygen will still have two bonds, not three, so everything will still be neutral. And this will make your ketotautomer, which is your final product here.